Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about a core topic of engines for reusable rocket and take an overview of multiple rocket engines that we use right now. So fundamentally, you have to understand what exactly is your need. What do you need from a normal engine versus a reusable engine? What is your core criteria? Criteria number one is deep throttling, aka rocket engines are like F1 engines. They always run at full power. There is no point where they are like throttling down. It's not like a car engine where there is a green zone. It's like always red 100% of the time. Now be mindful, even with normal engines, even with old engines, they do have some throttle capability. Let's say 100% is their full power, so they will have the ability to go down to as low as 90%, specifically if they are crossing the max q. So for stability reason, they will have some throttle capability. It's not like complete throttle, but they will have some control. However, for reusable rockets, specifically if you want to land that rocket, or even if you want to control the trajectory while you are falling from space, you have to understand you have exhausted most of your propellant, so your rocket is much lighter. So if you go full bonkers, you may mess up the rocket. So fundamentally you have to have the delicate hand, so to say. So you need something that has very large throttle range. See, basically 100 to 90 super easy. Almost every rocket engine has that. 100 to 70, now you are talking something serious, requires a redesign. 100 to 30, that is the maximum theoretical range, because you have to understand there is no like a throttle body in a rocket engine. Basically all they have to do is control the turbo pump. Now because turbo pump in many systems are closed loop, if they mess up that turbo pump, they could create a feedback loop where it no longer works on its own. So fundamentally there is a risk of what we call stalling. So deep throttle requires a complete re-engineering. You have to sit down with that engine. It's like, okay, how the heck I'm going to give you a throttle capability? It's not just like, oh, this is the engine, this is a reusable rocket system. It's not gonna work. You must have throttle. Another aspect, it must use liquid propellant. Now that is super simple. It's simply because you can refuel a liquid system. You can't do that with solid booster. NASA did try to reuse solid boosters of space shuttle. It was very expensive. It costed so much. They're like, dude, it would be literally simpler if you just made a new one. So fundamentally you have to understand that it has to be liquid system. And even hybrid won't work, because you have to design in such a way where you can physically remove one chunk of an engine, which we call fuel grain. So fundamentally you have to use a liquid system so it can actually be reused. Another aspect, multiple reignition is needed. If you look at Soyuz systems, they have a match on the bottom of the rocket and it goes push. So it does work, everything is awesome about that. However, if for some reason you want to shut down the engine, it's like, okay, it has dumped the payload into the orbit, let's close the engine and let's coast for a bit and then reignite it. The engine is like, nope, you can only turn me on once, like once, that's it, done. So you want what we call multiple reignition capability. Even if you want to do something like, let's say, electron rocket, where they want to use parachute to capture it, you do want the ability to reignite it so you can control the descent. So fundamentally it's a very compulsory requirement. Then quick turnaround time. This was the fundamental flaw of space shuttle, where they were like, okay, it's awesome, it's reusable, it's just, it takes 2 freaking years to turn around. So fundamentally you can understand that it's not a desired thing. Basically you want your engine to be like, okay, engine has landed, let's let it cool down. Again, it's almost working at melting temperature, so it's a hot thing. Let's cool it down, let's scan it, let's figure out all the sensor log, all the data, do a thorough scan and be ready in 1 week. That's the aim. And maybe someday in future, maybe as quickly as, let's say, a day, so to say. But turnaround time has to be kept low, otherwise there is no point in it. Because human labor on a rocket system is very expensive, because rocket scientists are very, very expensive. So this is what we need fundamentally. Now let's look at the first system, RS-25. Now RS-25 is first large scale, as in like not for small toy prototype, no, huge engine with huge capability reuse engine. Now this puppy was used with space shuttle. It was very successful, and it was using liquid oxygen and liquid hydrogen. Benefit of this, while it does have less oomph, it does not have a GG amount of thrust, it does have clean burn. What does that mean? That simply means the engine degradation while you're running it is very minimal. And engineers who were responsible for refurbishing this, they were like, it was always steam clean. Why? Oxygen plus hydrogen equals water. Water at such high temperature equals steam clean engines. So it was quite clean. So it did have some advantage, and this is surprisingly complex in terms of engineering wise, and NASA achieved almost unthinkable closed cycle engine back in that day. And it had electrical ignition system. So basically ignition can be done from the inside system. You did not need a match, and whenever you see the launch pad and you see those sparks will go, flying sparks, those are not for ignition. Those are because hydrogen is a leaky fuel. It leaks 100% of the time, every time. So it's supposed to leak, and those sparks will supposed to set them on fire before it pools up and it becomes becomes a big boom hazard. You don't want big boom hazard. So fundamentally, that's why those spark splits are there. But the core engine start happens from the inside. It has an electrical furnace, to say, which has like very small amount of hydrogen, very small amount of oxygen, so it can actually be ignited with electrical system. So it had electrical ignition system. I'm not sure whether it could be reignited in space or not, but fundamentally it does have the capability. So we are talking about RS-25. Then we come to BE4. Now, be mindful, this engine is shrouded in mystery because again it was cleared for Department of Defense. So it uses liquid oxygen. Almost every rocket engine uses that, and liquid methane. Now this is kind of a new kind of era, so to say. Fundamentally, you want to use hydrogen for clean and high efficiency, basically how fast you can go. But because hydrogen is a light element, it does give you speed but does not give you the oomph where you like, okay, I can carry 10 ton. It's like, bro, I can't do this. So you want something where you want a bit of balance. So if you go kerosene, you have a lot of carbon. You're like, dude, I can send things to the moon. Consequence, it's not very efficient. It cannot do very fast things. So even if you are using kerosene, like in case of Saturn V, your third stage still would be hydrogen based, simply because you need the speed. So these are the two options you have: clean hydrogen and hydrocarbon. So somebody's like, what if we go closer, because hydrogen almost does what you need to do. What if we add only one carbon to it, aka methane, aka, here's the interesting part, compressed natural gas or liquefied natural gas or just liquid gas, basically natural gas. So fundamentally, methane is a mass production equipment, so you can just buy it. You don't want to, like, okay, take kerosene, refine it to basically jet fuel level, then refine it to rocket level, then you will have something like that. And here it's just like, yeah, take it, done. So that's why they want to use liquid. It's surprisingly cheaper. It's a closed cycle system, which nowadays is kind of necessary because it gives you the most efficiency possible, and it has electrical ignition system, so it has multiple reignition capability. Because even if a Vulcan rocket that's going to be used next year, so to say, does not intend to be reusable rocket, but the Blue Origin's own rocket will use this puppy as a reusable system. So fundamentally, they do need this system to have the ability to reignite mid-flight. So it's like once it's gone there, it's like supposed to reignite. It's not needed in Vulcan, basically. It's not needed for Atlas replacement, but they need to have that technology. Now, core reason why this engine is like so interesting, not because it's already done or finished or something like that, is simply because their design goal is 100 uses. That's a lot. Fundamentally, to give you a context of that, Merlin engine, it basically poops out at 10. So fundamentally, this is a very big achievement. Now again, it's a design goal. On paper, they have not reached orbit yet, so it's still yet to be seen whether they can actually pull this off or not, but time will tell. Then we come to the Merlin. Now Merlin is first commercial reusable engine. Now be mindful, Space Shuttle did have reusable engine, but the engine was never reignited and it landed using wings, not engine. This is the first time engine was used as a landing system. So fundamentally, it was one of the greatest achievement at this point in time. So because it fundamentally allows us to land rocket effectively. So it's awesome. It uses liquid oxygen, but uses liquid kerosene. The thing I specified, hydrogen gives you a lot of basically speed, but does not give you oomph. Kerosene gives you a lot of oomph, and they needed a lot of oomph for, they are making the first rocket. You better build it over spec than under spec, so they used kerosene. Now kerosene does have one side effect. The output is very sooty because carbon chains, extra hoo-ha, you don't want that. The output is very sooty, so they had open cycle. Benefit, simple engine. Side effect, low efficiency. And basically kerosene and liquid oxygen, if you mix them, common sense will say it will set on fire. But here's the thing you have to understand: for ignition, you need three things: heat, fuel, and oxidizer. You have fuel and oxidizer, and given the fact that liquid oxygen is so cold, it will freeze kerosene. You can understand that point. Like, it will not catch on fire very effectively. So they had to use something else, third party, which is T-tab. Now T-tab does work. It's a pyrolytic system. Basically, it touches oxygen, it will ignite. Does not matter whether it's space, undersea, or wherever you want to. Like heck, it's been used in some fighter systems also. Fighter jet system to reignite engines in very high altitude. It does work. It's absolute. Problem, you have to carry a third system, like where it's like, okay, you have basically kerosene, liquid oxygen, and a third tank, which they had issues with in the past, where they ran out of T-tab and engine failed to reignite. So fundamentally, it's a weak point, so to say. And kerosene, sooty output, and that's why Falcon 9, I'm saying, when it goes on a launch pad, it's like completely new, it's awesome white. By the time they reuse it, it's like black, simply because of the sooty output of an open cycle system. Now we'll talk about the replacement of Merlin, Raptor engine. Now Raptor engine is using liquid oxygen and liquid methane, because methane is the next thing, simply because it has the most advantage of hydrogen and most advantage of kerosene. So they're going the same basically BE4 route. However, it's a closed cycle system, exactly like all modern systems, and it has electrical igniter, so it can ignite on its own. It does not need T-tab. That is a very crucial requirement because you cannot refill T-tab on Mars. So fundamentally, it has to have that. And you have to understand that they are coating, aiming for 50 reuse cycle. Now that's much better than their 10 one. So again, a lot of improvement, awesome things. But you may think, wait a minute, that's not too high, and that's a Gen 2 product. You may expect like 10 times improvement or 20 times improvement, but you have to understand they are going for something very unique. Elon Musk's philosophy is like, in terms of manufacturing, make the thing manufacturable. Saturn V was amazing rocket, but it was flat out unmanufacturable. So to manufacture that, it costed exponentially more. To achieve the same thing with a system which was designed for manufacturability, you can bring down the cost, and that's the whole point of SpaceX. It's like bring the goddamn cost down. So they figured out, their early research was like very simple: make smaller engines. More engines is much more efficient than making one giant engine like F1 engines. So they are doing the same, only they are increasing the engine size little bit. It's still using the same factory. They do not need to build giant factories to handle this same kind of thing. However, they are going bonkers on high power to weight ratio. Basically, if they go with this route, small engines, awesome. Russia wanted to do that with their Anagia rocket. Everything is awesome. N2 rockets, pardon manga. It works, it's awesome, but it has idiotically large amount of complexity. And anybody who does engineering will tell you this core principle of engineering: complexity is the enemy of reliability. The more systems you have, the more hoo-ha will happen, the more things will go boom. You do not want that. So fundamentally, how the heck you make small engines and yet send a large payload to orbit? You make per engine much more powerful. How much powerful? High power to weight ratio. This at this point in time, highest achievable. Fundamentally, there is nothing that even comes close to the power to weight ratio. Basically, this puppy is, let's say, for example, is 10 ton, it can carry 200 tons. So it's bonkers at this point in time. So that's why Raptor does not have like that kind of longevity. It's not designed for like 200 reuse cycle, but it is a like very powerful puppy. So, and it should, in theory, should be able to pull off, basically take off, land on Mars, and come back. Now, as in like a lot of refueling has to be done in between, but it should be doable. So these are the 4 engines that we utilize in current rocketry. So this was my small presentation of like just giving you an overview of multiple reusable rockets, the engines that we use at this point in time. I hope you liked it, learn from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, I would urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.